Hello guys, let's start aldehyde ketone and carboxylic acid from NCERT Neet point of view, or we can say we will discuss some questions also from Neet or JEE main point of view also. So first of all, we have to understand what are aldehyde ketone and carboxylic acid. So there is a group that is called carbonyl group, C double bond O. If one valency of carbon is always occupied by H, then that is called aldehyde. If one valency of carbon is occupied by R, means alkyl group or carbon chain, and another valency of carbon is also occupied by R, means carbon chain, then that is called as ketone. So that is ketone and that is aldehyde. And if we occupy one valency of carbonyl group from OH, as you know, then that is called carboxylic acid. And there are number of derivative of carboxylic acid, for example amide. So if one valency of carbonyl group is occupied by NH2, or we can say if we replace OH group with NH2 group, then that is called as amide. If we replace carboxylic acid OH group with OR, then that is called ester. And if we replace OH group of carboxylic acid with X means halogen atom, then that is called acid halide. Acid halide. So these all, acid halide, ester and amide, all are the derivatives of carboxylic acid. So that is aldehyde, ketone, carboxylic acid, acid halide and amide. Another is ester. If we replace carboxylic acid OH group with O, C double bond O, R, so that compound is known as anhydride, or we can say acid anhydride. So we can say there are lot of derivatives. Which one are derivatives of carboxylic acid? Ester, acid anhydride, acid halide and amide. These are the derivatives of carboxylic acid. So if we are uh, getting the nomenclature of aldehyde, so that is called benzaldehyde, acetaldehyde, beta bromobutyryl aldehyde. These all are common naming system. But if we are coming at IUPAC nomenclature, then on is the suffix which we are used for ketone, and L is the suffix which we have to use for aldehyde. So that is the IUPAC naming. Like ethanol, that compound is called 4-bromo, because aldehyde is terminal functional group. That's why we have to start our numbering from this carbon: 1, 2, 3, 4, 5, 6 as well as 7. These all are the IUPAC nomenclature. If we discuss the carbonyl group, structure of carbonyl group, then we can understand the carbon present in carbonyl group is sp2 hybridized. And we all know in sp2 hybridization, the structure is trigonal planar. That's why carbonyl group structure is trigonal planar shape. Trigonal planar shape. And bond angles are approximately 120 degree. So that is the structure of carbonyl group. This carbonyl group carbon double bond oxygen is polarized due to electronegativity of oxygen. So pi bond electron will be shift towards oxygen. That's why oxygen will get negatively charged and carbon become positively charged. Preparation of aldehyde and ketone. First of all, the first method of preparation of aldehyde ketone is the by oxidation of alcohol. We all know that if we have 1 degree alcohol or primary alcohol, then we can convert it into aldehyde. If we use selective oxidizing agent like PCC, PDC, pyridinium chlorochromate, pyridinium dichromate, but if we are using a strong oxidizing agent like KMnO4 or K2Cr2O7, then this 1 degree OH gets converted into carboxylic acid. But 2 degree alcohol or secondary alcohol, when we oxidize using KMnO4 or K2Cr2O7, it gets converted into ketone. Number of carbon in aldehyde and ketone would be same as in alcohol. Next one is method of preparation by dehydrogenation of alcohol. Dehydrogenation means removal of hydrogen. For removal of hydrogen, we can use copper at 573 Kelvin temperature. So if we use copper at 573 Kelvin temperature, then 1 degree alcohol gets converted into aldehyde and 2 degree alcohol gets converted into ketone, and number of carbon in aldehyde and ketone would be same as present in number of alcohol. So if we are using copper at 573 Kelvin temperature, it is used as a dehydrogenating agent, means it will remove hydrogen. Another method of preparation of aldehyde and ketone is by ozonolysis of alkene. We all know if we do ozonolysis of alkene, so if we use ozonolysis, means first step ozonoid will form, and if we treat this ozonoid with zinc and H2O, then we will get aldehyde or ketone. So this bond will be break and we will get like this. The groups present on in these vacancies will be same. For example, if here is R, here is R dash, here is R double dash, and here is R triple dash. So there is R, R double dash, R triple dash. So group attached to carbonyl carbon would be same as present in alkene, alkyl group or hydrogen. Another method of preparation is by hydration of alkyne, that we have also studied in 11th class in alkyne chapter. So if we are using any alkyne, for example R C triple bond CH, then if we do addition of water in the presence of Hg plus 2 ions, then this bond will break and we have to add here, no, this bond will not break, actually we have to directly add here R C double bond O, and that one is CS3, so that we will get on hydration of alkyne. Another method of preparation of aldehyde is from acyl chloride or acid chloride. So first one is Rosenbond reduction reaction. In Rosenmund reduction reaction, we can understand we have to take the reagent PdBSO4, palladium, BSO4 and hydrogen. So that reagent name we have to remember. In this reaction, COCl group gets converted into CHO. COCl group that gets converted into CHO. That is called Rosenmund reduction. Next one is Stephen reaction. In Stephen reaction, again cyanide group gets converted into CHO group. We have to use SnCl2 plus HCl as a reagent, and this this imine will be intermediate of this reaction. Another method of preparation is we can directly get converted cyanide into CHO by using dibel. Dibel means diisobutyl aluminum hydride. That is a selective reducing agent. That is selective reducing agent. It reduces cyanide group or ester group group. Both group, cyanide group as well as ester group, both group gets converted into CHO aldehyde. In this example, we can understand this cyanide group gets converted into CH. Double bond, triple bond, these bonds are not affected by dibel, diisobutyl aluminum hydride. So double bond in reactant as well as in product will be intact. Similarly, ester, that is the ester gets converted, this bond will be break and we will get this aldehyde. So ester can also affect by dibel as well as cyanide also affect by dibel, but double bond or unsaturation will not affected by dibel, diisobutyl aluminum hydride. That's why it is a good selective reducing agent. Next one is from hydrocarbon. Yes, we can convert hydrocarbon also in aldehyde or ketone. We all know if we use any alkyl benzene like CS3 and if we use a strong oxidizing agent like KMnO4, then the CS3 group gets converted into COOH group. So we will get benzoic acid. But it is a strong oxidizing agent. But if we use mild oxidizing agent, then we can stop the oxidation at aldehyde stage by using suitable reagents. What are these reagents? First reagent is chromyl chloride. So if we use chromyl chloride, then our methyl benzene gets converted into benzaldehyde, means we can stop the reaction up to aldehyde level. So first one is Itard reaction. What is Itard reaction? In Itard reaction, we use toluene and chromyl chloride CrO2 Cl2 react in the presence of CS2. This chromium complex is formed and our ultimate product is benzaldehyde. Next one is chromic oxide. If we use chromic oxide in the presence of acetic anhydride, then we can also convert this toluene into benzaldehyde. Another example is by side chain chlorination followed by hydrolysis. So what is the meaning of that? If we use toluene, we can convert it into benzyl chloride first of all by using chlorine in the presence of HNO. Here is free radical substitution reaction will occur. Free radical. We get benzyl chloride and on the hydrolysis of benzyl chloride we get benzaldehyde. Another one is by Gattermann-Koch reaction. In Gattermann-Koch reaction, we treat benzene with COHCl and the presence of anhydrous AlCl3. Here we can also convert benzene directly into benzaldehyde. That reaction is known as Gattermann-Koch reaction. Another example, another method of preparation. That method of preparation is specially for ketones, only for ketones. It's not used for aldehyde. For example, we have studied Rosenmund reduction, Stephen reaction. These are the method which are used only for aldehyde, like that. Stephen reaction only for aldehyde, as well as Rosenmund reduction, that is also only for aldehyde. So these are the method which are used only for preparation of aldehyde. But if we are using the method of preparation like that from acid chloride, that method is only for ketone. So first of all, we have to treat Grignard reagent with CdCl2. It is used for preparation of dialkyl cadmium. So we will get dialkyl cadmium, that is dialkyl cadmium. If we treat that dialkyl cadmium with acid halide like R-COCl, then we can understand that Cl will replace by alkyl group of dialkyl cadmium, and we will get a ketone. In this ketone, one alkyl group is from acid halide and another alkyl group will come from dialkyl cadmium. So this method is only used for preparation of ketone. Another one is from cyanide. We can use cyanide and we can treat cyanide with our Grignard reagent. That is a step up reaction. That is step up reaction. Means number of carbon will increase. Now what happen? The electron of this pi bond will move towards nitrogen and nitrogen will carry negative charge, partial positive charge will be carried by carbon, and this bond will be split and alkyl group will get attached to carbon and MgBr will attach to just nitrogen atom, and if we do hydrolysis of this intermediate, then we will get our ketone. Another one is the Friedel-Crafts acylation reaction. Like we can use benzene and Friedel-Crafts acylation reaction RCOCl. We can use as a acylating agent in the presence of anhydrous AlCl3. Anhydrous AlCl3 is used as a Lewis acid. So anhydrous AlCl3 here used to create electrophile. So because it is electrophilic substitution reaction, so in this reaction we can also get convert benzene into ketone. So that is a specific method for preparation of ketone. If we study the physical properties, so in physical properties we know methanol is a gas at room temperature, but ethanol is a volatile liquid, and other aldehyde and ketones are liquid or solid at room temperature. If we discuss the boiling point of aldehyde and ketone, because in aldehyde or ketone there is dipole-dipole interaction. Dipole-dipole interaction. Intermolecular force of attraction in aldehyde and ketone are dipole-dipole interaction, which are stronger interaction comparable to London forces or dispersion forces which are present in hydrocarbon. So if we compare hydrocarbon and aldehyde or ketone, so aldehyde and ketone have higher boiling point than hydrocarbon, because in hydrocarbon there is a intermolecular interaction, that is London forces or dispersion forces, that is weaker compared to dipole-dipole interaction. That's why boiling point of aldehyde or ketone is higher. But alcohol, if we compare aldehyde and ketone with alcohol, comparable mass of alcohol, then alcohol have stronger hydrogen bonding. That's why alcohol have more boiling point compared to aldehyde and ketone. We can observe like that. Propane 1-ol, that is alcohol, its boiling point is 370. But if we compare propanol, that is aldehyde, as well as ketone, propanol have 322 and acetone have 329 boiling point, and ether have 281 because ether also have dipole-dipole interaction, but N-butane have least boiling point, that is 273. It's because in N-butane the interaction is London forces or dispersion forces, and in these all the interaction is dipole-dipole interaction, and in propane 1-ol the interaction is hydrogen bonding, and hydrogen bonding is stronger interaction. Then dipole-dipole, after that least interaction is, that is London forces or dispersion forces. Similarly, we can say the lower member of aldehyde or ketone can make hydrogen bonding with water. That's why they can miscible with water. They are miscible with water. Now comes at chemical properties or chemical reaction of aldehyde and ketone. So we can understand the aldehyde and ketone give nucleophilic addition reaction because the carbonyl group is a polar molecule. Electron of pi bond can move toward oxygen in the presence of nucleophile. And nucleophile, that's why carbon will be partial positively charged and oxygen get partial negative charge. That's why nucleophile will attack on partial positively charged carbon atom, and that is the rate determining step. That's why that is known as nucleophilic addition reaction. So if we do nucleophilic addition reaction, then carbonyl group, carbon is first of all sp2 hybridized, but when nucleophile add here, then its hybridization change to sp3. That's why its shape become tetrahedral shape. So, and that is the first step. So in first step nucleophile attack, and in second step the H plus ion will attach to oxygen atom. So first step is slower step. So that's why that is rate determining step, means attack of nucleophile on carbonyl carbon is a rate determining step. That's why that is called nucleophilic addition reaction. If we discuss the reactivity of aldehyde and ketone, then we can understand carbonyl group actually gives nucleophilic addition reaction. So in rate determining step, nucleophile attack on carbonyl carbon. So if here steric hindrance is more, then attack of nucleophile will be slower down. So if we attach a bigger molecule or molecule having larger atomic or molecular mass at carbonyl carbon, then nucleophile attack on carbonyl carbon slowly, so rate of reaction will decrease. That's why we can understand if we compare aldehyde and ketone. So aldehydes are the more reactive toward nucleophilic addition reaction because in aldehyde there is only one H is present, so less steric hindrance towards carbonyl carbon. In ketone there are two bulky alkyl group is present at carbonyl carbon, that's why more steric hindrance, that's why nucleophile attacks slowly. So aldehydes are actually more reactive compared to ketone in nucleophilic addition reaction. Similarly, if we compare benzaldehyde with propanol, then in benzaldehyde there is carbonyl carbon. That carbonyl carbon is attached to this benzene ring. There are two reasons by which we can say that benzaldehyde is less reactive. Benzaldehyde is less reactive and propanol is more reactive compared to benzaldehyde towards nucleophilic addition reaction. The first reason is that in benzaldehyde there is a bulky phenyl ring is attached. That's why nucleophile will attack on this carbonyl carbon slowly. The second reason is that why nucleophile attack on carbonyl carbon. Why nucleophile attack on carbonyl carbon? We have to understand. First, electron of pi bond move toward oxygen. That's why we can understand this carbonyl carbon become electrophilic. If electrophilicity of carbonyl carbon is increased, then nucleophile will attack on this carbonyl carbon faster. But in the case of benzaldehyde, there is a conjugation. That's why phenyl ring give its electron to this carbonyl carbon. That's why it decrease the electrophilicity of carbonyl carbon. In the case of benzaldehyde, the carbonyl carbon is less electrophilic because that phenyl ring provide electron to carbon. That's why benzaldehyde is less reactive towards nucleophilic addition reaction compared to propanol.